Right, okay, we're going to look at projectiles now. Projectiles is one of those things that people get always excited about. They're like, oh, projectiles! These can pose the biggest problems. Now, there are some examples on the YouTube channel of some exam questions. I will do some examples over the next couple of videos as well, because this will take a couple just to make sure we get everything done and dusted. So first of all, what is projectile motion? So a really simple explanation is where we've got you could say a golf ball, something like that that's projected upwards and horizontally at the same time until it goes back down and hits the floor. So golf ball, football, anything of that nature undertakes projectile motion. Now, what we observe as it goes on is that we need to understand what the velocity, what the acceleration is doing, where it's accelerating and where the velocity is changing. So I'm going to draw a number of arrows on this diagram to describe them. I would recommend in your notes that you have those arrows in different colours as well, just to aid in your drawings and your notes. So it starts off with an initial velocity in that direction. Now that initial velocity is going to be made up of a horizontal and a vertical component. And yes, you can do a vector resolution to work out what that is. So if we've got our initial velocity up there, then that velocity is going to be made up of a horizontal and vertical component. And should you know that angle, you can use trig to work out what the horizontal and vertical components are. So, as with this, we've got a horizontal and a vertical component of this velocity. Now, as the ball is travelling along its journey, one of these velocities is going to change. One isn't. Now, I will say this before we carry on. Air resistance is negligible in this case. We will look at some examples where air resistance might not be negligible, but for the most part here we're going to suggest that air resistance is negligible. So we're going to, as the ball travels along its journey, look at this ball velocity at varying points along the journey. So what are the vertical and horizontal components of the velocities doing as we go from here to here to here to here to here to here to here, all the way along? Well, let's look at the horizontal one. Ask yourself, in that direction, is it accelerating or decelerating? Now notice that it's travelling in that direction. Is anything going to cause it to accelerate or decelerate? The answer should be no. Nothing's going to cause it to accelerate or decelerate because what I've just said, there is no wind resistance. So no wind resistance. So that means that this vertical component, this horizontal component is going to stay constant throughout the entirety of the flight. It's not going to change at all. It's going to stay exactly the same. The horizontal component of the flight is going to stay exactly the same. Can we say the same thing for the vertical? Imagine for a second, I throw a ball up into the air. Think about what it does as it goes straight up into the air. I throw it initially. It starts to slow down until it reaches the very top of its height, in which case it will become stationary very instantaneously and then change direction and start accelerating downwards. So I've already used the word to give it a clue there, so it's going to be changing velocity. So it starts off with a high velocity and then it's going to get progressively smaller until it has no vertical velocity at all. Okay? No vertical velocity. What happens after it's reached this mid position? Well, that is because it starts to accelerate downwards. So, what we're going to observe is the opposite of the other side. We're going to see the resultant get bigger until it matches what we started with, but in completely the opposite direction, as long as air resistance is negligible. So this velocity here, numerically, magnitude-wise, is exactly the same as this one here. The only difference is that one is minus and one is positive. So that would be the resultant, the velocities all the way through. Now that makes sense, because if you look at the resultant in each case, the resultant matches up with what you'd expect the ball to be doing at each point along its trajectory. So now, what is the acceleration doing? Now the acceleration, I was just looking for another colour pen, but I haven't got one on me, so I'll just stick with the red. Now the acceleration found it. So the acceleration is going to be the same all the way along this throw. Now you might be thinking, well, how can that be possible? Well, wherever you are on Earth, you're being pulled down by the force due to gravity. There's no difference here. When we look at Newton's second law and Newton's laws, that will make a little bit more sense. But the acceleration downwards due to gravity is constant throughout this flight. It does not change. It doesn't change. It's always being accelerated towards the ground. Think about that in terms of velocity. The velocity is decreasing vertically as it goes up because the acceleration is always directly downwards. The velocity is increasing when it passes the midpoint because it's still being accelerated downwards. It's just travelling in the same direction as the acceleration. That's why we're getting an acceleration. So you could consider it to be deceleration, acceleration, whereas the magnitude of the acceleration is always the same value no matter what is happening in this situation. So as you can see here, I've drawn all the lines on there, but you need to be clear about what each one is doing. Horizontal velocity stays the same. Vertical velocity changing. Acceleration, as long as we have no air resistance, is always the same. Okay? So this quite nicely should be a diagram that you have in your notes. You should know what the velocity is doing vertically, horizontally at any point, and you should be able to understand that at each point we can draw a vector resolution to show what the resultant velocity would be in each case.